All right, all right. Okay, so last time we had talked about this guy, Bm equal I over nabla, and Bm helps us determine the stability of our hull. And then we said, okay, let's look at using that Bm, we can compute Gm. Okay, Gm basically gives us what's the restoring torque. If Gm is positive, we get our hull is stable. Okay. If GM is negative, our hull goes unstable. And the reason is even a small tilt will cause our hull, the torque, to be to make it worse. If GM is equal to 0, which rarely happens, this is what we would get. So this condition we call neutrally stable. Oh wait, there's a chat. Oh, that's fine. Okay. All right. So let's see. Let's draw another sketch here. And center line, we have keel, buoyancy, we have G, and we have M at the same. All right. And when we know our new B prime would be somewhere here. So in this scenario, what happens is we get our buoyant force acting up here, FB, and our weight acting straight down here. And you see there's no lateral separation between the two. So there's no restoring torque or a torque that would make it unstable. So no lateral separation. And this means we have no restoring torque. Or destabilizing torque. All right, and you might have seen images of ships just tilting sideways and staying there. And well, that's mostly because they've loaded their cargo incorrectly. But in that scenario, it's a slightly different scenario. So this is very unlikely to happen, this neutrally stable case. Okay. Whenever you design a hull, you should always try to make it as, GM should always be positive. You must not let this happen because the boat will capsize. Okay. So now let's quickly see Bm equal I over nabla. This is a very important one that we'll use over and over. Let's see where this comes from, and then we'll do some examples of hulls loaded, and we'll compute how stability is affected. So to figure out, to determine why Bm is I over nabla, the first thing is, let's say I have a square plate. And from this plate, I cut out a smaller square section and move it over here. Okay, so you cut out a corner and attach it over here with glue or something. And initially, we had x1, area 1. The piece we cut out, let's call its center x2, area 2. And where we move it, we call it x3, area 3. Well, area 2 is equal to area 3, so this. We're just talking about the x coordinate. Of course, there will also be the y coordinate. So do you remember how we compute the new x centroid, x combined? Okay, so you're saying add all three? One change. You see, you have cut out an area and you have removed it. Yeah, so this part you would have a negative. Okay, everything else remains the same as we had. So the combined area, combined centroid would be at x1 a1 minus x2 a2 plus x3 a2. Okay. You see the total area remains the same. It's in the bottom, just to make it obvious. We didn't change the area. We just cut out one piece and moved it and attached it elsewhere. So the total area remains the same. Similarly, you can compute the y centroid. It's basically y1 a1 minus y2 a2, y3 a2. And this here we have done it for a flat object. So just talking about the area. The same thing we could have done with volume. If this were a box and you cut out one corner as a three-dimensional smaller box, move it elsewhere, the xb, yb would be computed similarly. B, for us, B is the center of buoyancy, which is always the center of the volume. Okay, so that's why I called that B. So we will use this concept now. So we will use this concept to demonstrate that Bm is equal to I over nabla. Yeah, in naval architecture or ship hydrodynamics, this is one of the most important ones. Simple, but very important. All right, let's draw a sketch of an inclined hull. Let's draw it big because we'll have to annotate many things. Marking the center line. This is our new water line. Our old water line used to be this. By old water line, I just mean when the hull was upright, this would have been horizontal with respect to the hull. Now the hull is tilted, water level doesn't tilt. Okay, so this is new water line, and that we have the old water line. This shaded part that I will draw is what has emerged out of the water. Okay, so this, let's call this volume emerged. And similarly, this part over here is the new volume submerged. And they have to be equal because the weight, total weight of the ship, the displacement hasn't changed. So the total submerged volume should not change either. So whatever comes out has to be submerged on the other side. And if we say the roll angle is phi, if this is 5 degrees, then this is also 5 degrees. And let's call this distance is y. The centroid of this triangle is 2/3 of y. This base or height of the triangle would be y tan phi, nearly equal to y times phi if the roll angle is small. And let's mark this as the centroid of submerged. Okay. Now let me mark, so this of course is the keel, and let's say our original B was here. And we know that when we tilt it, our B will have moved sideways. Let's call this B prime. Okay, so yeah, getting busy. One more thing I want to mark is where's the M location. So the meta center, remember, is always straight up from the buoyancy center. So straight up, somewhere over here would be the M. Yeah.
Would B prime rise at all, like go up a little bit, since the top of the corner of the ship is technically a little higher when you rotate it?
It forms an arc. It almost
Okay, yeah,
moves
so
in an
it
arc.
would technically a little bit.
Yeah, but for very okay. So in case you didn't hear the question, remote students, it was whether B prime should be slightly higher up because of the way the ship is tilted at the moment. So the B location actually describes an arc, a very smooth arc, right? And for very small angles, that smooth arc we assume is a flat line. Okay. So that's why I've drawn it lateral. And small angles again are required to make this assumption. Y times tan phi is y times phi in radians. Okay. So let me just pull down the paper just 1 second and look at this image. What did we do here? We cut out a piece and moved it to another place. Look at what we have done here. We've cut out a submerged volume and moved it to another place. Okay. So we'll basically use the same formula we had up there. So imagine that the volume emerged has been cut out, well, cut out in quotes. And been moved to a new location as volume submerged. All right. Now, so to figure out what exactly is the value of the volume we cut out, the cross section looks like a triangle. Okay, we know how to compute the area of the triangle, half times base times height. And when you integrate this all along the length of the ship, that would give us the volume of this wedge. So let's write that down now. Area submerged is half times y times phi times y. Okay. So base times height and half of that. Volume submerged would be and of course this is equal to volume immerged. It would be, so look, the sketch we have drawn is looking at one particular station of the ship. Imagine the hull would be coming out of the plane and into the plane. So x going from 0 to whatever the length is times y squared phi over 2 dx. This, if you can say this would be representative of what the midship plane looks like, but this we have just taken it to be a very general. We don't say x is at midships. This can be anywhere, and you can already see that this will, as you go to the fore and the aft, this would probably shrink a bit. Yeah, yeah. So this would squeeze as the hull gets finer. Okay, but we have our y squared, which is a function of x. So depending on what section you're looking at, that y would depend on x. So this integral is fine. All right. Then one more thing. Okay. We wrote here xc and yc equals something. We'll write the same for y, xb and yb. Well, yb mostly. So yb new is equal to yb original times volume original. Okay. All right, let's do the bottom first. That's easier. What goes on the bottom? Give me in terms of nabla, well, volume submerged, and volume immersed. What do you say it would be? Okay, then let me rephrase that. So original YB location was something. In this case, we know it's here, so YB is equal to 0. Now we've cut out a piece and glued it in some other place. We need to find out what's the new YB prime location. That's what we're trying for right now. Okay, let's subtract this guy. Yeah, so wait, let me just, there's 2 minus signs, so let me. Volume immersed, you subtract, okay? So what's the centroid location? It's negative 2 over 3y times nabla emerged. Okay. And then once we move it to a new location, it's a plus. Yeah, plus 2 over 3y nabla submerged. Yeah, and on the bottom, we have nabla minus nabla emerged plus nabla submerged. And since these two are equal, they will cancel. Yeah.
Oh, right, look, there's a location.
So this YB original location, it falls on the center line. So we know this is exactly equal to 0. And we'll be left with some stuff. So we have 4/3 y times nabla submerged over nabla total. All right, and nabla submerged we have here on top. So we'll just put that integration over here. So this is I've just nabla submerged or just that we had the integral here, and I've just incorporated that in this formula here. Okay, and what we end up with is this is 0 to L 2/3 y cubed dx over nabla. So when we tilt our hull, that is the new lateral position of our center of buoyancy. I missed a phi here. Phi is the constant roll angle, so we just take it out of the integral. All right, so this might look familiar to you, 2/3 y cubed over y cubed dx, but let's just look at the front view. And when we think about, so this is y and this is z, this is x. When you think about what is also ix is what? 0 to L, y is negative f of x to positive f of x, y squared dA. Okay. So that we know from our previous lectures. And you'll see that this simplifies to 0 to L y cubed 2/3 y cubed dx, or f cubed x dx. Okay. You can leave it as y or write f, they are the same thing. And you see this 2/3 f cubed is the same as what we have here, 2/3 f cubed. So the denominator, this term is basically Ix. So we get YB nu is phi times Ix over nabla. Okay. All right. So we're close to what we wanted. We have an I over nabla, but there's this phi in between. So let's see what YB nu is. This is YB nu. YB nu is B0 B prime. I'll remove the paper in 1 second. B0 B prime, which you can also write as B prime M times phi. Okay, again, trigonometry. The radial distance times the angle gives you the arc length. All right, and we just wrote this is equal to phi dot Ix over nabla, which gives us B prime M, which is very close to Bm equal to phi, oh, no phi, Ix over nabla. And that's the reason why we had Bm equal I over nabla. That's where it comes from. So Bm by itself is not the most useful thing to us. We care more about Gm. Remember, we were talking about when Gm is positive versus negative, what happens. So we can use this Bm to compute Gm. So once we know, okay, so let me just write one sentence and then we can stop. And yeah, next class we'll go further in how exactly to compute GM. Okay, any questions? I've posted homework too. It uses a lot of the stuff we're talking about right now. So take a look and ask me questions next week. Oh, next week? Today's Friday, right? Yeah, next week. Okay. All right, so see you guys later. Nabla is the volume. Delta is rho g times volume.
Yeah. Professor.
Yeah.
How many quizzes do you think we'll have this semester?
We'll have at least one more. Yeah.
Okay.
One more is what I want. Sometimes people ask me to give more quizzes.
Yeah. I think I confused my area moments of inertia. So.
Okay, but don't worry. I mean, I'll give out partial points for your steps.
Okay. Have a good day.
All right, you too.